Hello, this is Group 17, and this is our project demo for our Morse code translator. The goal of our project was to design a system that receives a message in Morse code through button presses, decodes the input, and displays the translated message on a screen. How the system works is, using the FPGA board and using a single button, you would enter your message in Morse code via different button press durations, and once your input is ready, you would then press a second button that will then have the system decode the Morse input by translating the dots and dashes into their corresponding letters and assigning it a number that the VGA will then take and will display the translated message on the screen for the user. Our Morse code project includes the following key features. The system supports the input and display of all 26 letters of the English alphabet, the numbers 0 through 9, and a space character for empty inputs, allowing the user to display a complete message on screen. The display is limited to up to 32 characters at a time, displayed in one single row, and once the screen is full, the system will no longer accept additional inputs until reset. Our system has a reset functionality where once the reset button is pressed, it will clear the screen and allow for new inputs. For a clean restart, ensure that the input is empty before pressing the reset button.
This photo shows our FPGA board layout, and in regards to the buttons, we use the outside 4 buttons. The top one we use as our VGA controller reset. The leftmost we use as our send button, which would send our input to our display. The bottom one, the bottom button, is our display reset, which resets all the letters on the screen. And then the rightmost button we use as our input button, which is where we would represent the dots and the dashes. On the bottom where the LEDs are, we use the rightmost 10 LEDs to show our inputs in real time. The first LED on the left we use as our clock, which would show the user at what time increment they should be holding their input button, and then the button right beside that is just a confirmation that the send button went through and it actually sent the input to the display.
Hello, this is Jacob, and I'm going to be giving an overview of the GitHub repository for our Morse code translator project. If you look over here on the side where my mouse is, we've got this organized with a couple of folders. In the constraints folder, we just have the constraints file. It's pretty simple. We just assigned ports sequentially. We have our LEDs on this side with the 10 LEDs on the right being assigned to these. I'll explain what these are later. And then we have the 2 left LEDs being assigned to these 2. We have our buttons assigned sequentially as well. I'll go over what these mean in a second. So here we have the wire declarations, and then here we have the important stuff, all the module declarations. So here's the VGA controller declaration. Here's the file itself. So what the VGA controller does is it takes in the clock and then a reset, the system reset that we use to scrub the screen, and what it generates is it generates an area on the screen that can have characters displayed on it. More or less just instantiates the VGA. So underneath that right here we have our clock divider circuit. This clock divider is the same one that Jessica used in her lab 2. It's the same one that was given to us, and we're operating at 1 Hertz because it's just easier to use that way, which means we didn't actually change anything from our lab 3 clock divider. It's the same exact file. It's also the exact same toggle parameter as it was for that project. And then underneath that, that's assigned to the clock LED, so that when the divided clock is in a positive state, the LED will light up. Over here we have the debouncer. I've tried this with my debouncer as well as Jessica's. This is Jessica's that's on the file right now. Both of them work I just chose to use hers because it was more consistent with the rest of the project. I'm not going to spend much more time on the debouncer. It's the same as the one that was used in the lab, relatively simple. If every clock cycle, it checks to see if the button's pressed. If the button is pressed and it was pressed last clock cycle, it starts outputting the signal. If the button stops being pressed, the signal obviously stops being sent. And it just makes it so that you have to hold down the button for more than one clock cycle in order to get an input at the next stage. So the button encoder is the next module here. And the button encoder takes in your inputs, your dots and your dashes, and then stores them in a 10-bit register right here. So when you put in your input, when you start holding down the button, you have to hold it down for 1 second or 2 seconds in order to get a dot. Where is that in the code? That's right here. It adds a dot. If you hold it down for 3 seconds or more, as dictated by this parameter, then it will append a dash to the 10-bit letter register. After the button encoders correctly collected that 10-bit register, it gets sent to the decoder, which is basically just a huge mux. It takes in your inputs and then gives out a specified code for each character, for every character that we have implemented to display. So here we have character 0, which is a space, character 1, which is an A, 16 is a P, 36 is a 0. So once the letter num has been determined by the decoder, it gets sent to the ASCII test module. This is ASCII test. What this does is it takes in the letter num and then it displays the appropriate character on the screen, and it also shifts over the position of the character so we can have more than one character on the screen at a time. The characters are the pixels of the characters are determined by this module, ASCII ROM, up here. It's basically just a big block of memory. Every pixel is assigned sequentially. This one is a space. Here's our A. We have different ones for all of these, all the way down to 0, from numbers 1 to 9, and from numbers 0 to 9, sorry. So that's about everything for the code for our project. Thank you for listening.
The following clip shows our translator being used. On the bottom of the FPGA, you can see the flashing light that we use as our clock, and we are using our translator to input the phrase hello 311 to showcase the alphabet functions, the space, and the numbers. And then you can see on the bottom, as we are inputting each letter, the corresponding 10-bit value is being displayed on the LEDs. The next clip is us showcasing our reset function, where we are inputting the letter E, clearing our display, and then inputting another letter. And this is simply just showing that our reset function is working.